This is the third lesson of Theory of Computation. In this lesson we will learn how an NFA can be converted to a DFA. Equivalence of DFAs and NFAs. You may have the impression that non-deterministic finite automata are more powerful than deterministic one. In this section, we will show that this is not the case. At first, we should know that a language can be accepted by a DFA if and only if it can be accepted by an NFA. What about converting a DFA to an NFA? Well, there is nothing to do, because a DFA is also an NFA. Let n equals capital Q, capital sigma, delta, lowercase q, and capital F be a non-deterministic finite automaton. There exists a deterministic finite automaton M, such that language M equals language N. Let the DFA M be defined as M equals capital Q prime capital sigma delta prime lowercase q prime and capital F prime, where the set capital Q prime of states is found by power set of capital Q. The start state lowercase q prime is determined by considering epsilon transitions of lowercase q. All the elements of the set capital Q prime that intersects with the set capital F are assigned as the elements of the set capital F prime. But perhaps the most important and difficult one is the definition of the delta prime transition function. We will learn it in detail on the example. In this example we will convert the NFA problem for which both the transition diagram and the table of the delta function are given to DFA. Notice that there is one epsilon transition, two missing transitions, and one extra transition in the question. First set of states capital Q prime is easily determined by using power set of capital Q. Because of all subsets of capital Q, the number of elements in capital Q prime will be 8. Writing the start state lowercase q prime is also simple. When we look at the first row of the table we see an epsilon transition. It means that lowercase q is the state 1, but when we start the automaton it can arbitrarily pass and start at the state 2. The third one is to find new accept states. Here we can again look at the table. We know that the state 2 is the only accept state in NFA. Therefore in the set capital Q prime we mark all new elements which contain 2 as the accept state. Now it is time to define delta prime. However, many of my former students in this course said me that the method used in our lecture notes was not easy. Since they suggest using the table method, we will learn it now. First, write all the elements of the capital Q prime as the label of rows and input symbols as the label of columns. The first row in the table should be filled with empty sets. It will be our black hole reject state. When you go there, never gonna escape. Then import the partition matching the NFA into the table exactly. Ignore the epsilon column in this section. Now use the epsilon column and update the section you just filled out. Here, since there is a epsilon transition to state 2 from state 1, add 2 wherever you see 1 in the table on the right. Last, fill the empty elements by using union operation among the filled elements. Now our DFA solution is ready. However, this may also include some unnecessary states. We can make an optimization so that we can delete unnecessary states. Starting from the initial state Q prime, all possible states are marked. Unmarked ones are deleted. Finally, we found a DFA with only 4 states. Now we can draw its transition diagram. Here we have both the table and the transition diagram of the DFA solution. That's all. Thanks for listening.